Hello friends, welcome back to my channel. Today I would like to share with you the concepts from Equilibria, chemical equilibria, reversible reactions and dynamic equilibrium. Reversible reactions. A reversible reaction is one which can proceed in both directions as indicated by the reversible arrow sign. For example, H2 plus I2 gives 2HI, 2SO2 plus O2 reversible to SO3. In a reversible reaction, the reactants react to form the products. The products in turn also react to reform the reactants. A mixture of reactants and products is present. An equilibrium is established between them. Characteristics of equilibrium. It is dynamic. Dynamic equilibrium is a situation where the rate of forward reaction becomes equal to the rate of reverse reaction, and the amount of substance present do not vary with time as long as the conditions remain the same. In the microscopic scale, the reactants and products are continuously reacting, but in the macroscopic scale, there seems to be no change at all. The concentrations of the reactants and products remain constant. This is because at equilibrium, the rate of forward reaction equals the rate of backward reaction. For example, H2 plus I2 reversible to HI. At equilibrium, for every 1 mole of the reactants get converted to 2 moles of products. 2 moles of the products are reforming the reactants. The graphical representation is shown here. It requires a closed system. A closed system is one which none of the substances can be added or removed, but energy can move in and out freely. In an open system, the products formed will escape. This will not allow them to react and reform the reactants, and equilibrium will never be reached. Factors affecting chemical equilibria. Position of equilibrium. Position of equilibrium refers to the relative amount of products and reactants present in an equilibrium mixture. Le-Chatelier's principle. Le-Chatelier's principle states that if a change is made to a system in equilibrium, the system reacts in such a way so as to oppose the change, and a new equilibrium is established. In other words, whatever done to the system does the opposite. Effect of change in concentration. When something is added or removed, the system will do the opposite so as to remove or replace it. When the concentration of A or B increases by Le-Chatelier's principle, the position of equilibrium shifts to the right to decrease the concentration back. More C and D are being formed. When the concentration of A or B decreases by Le-Chatelier's principle, the position of equilibrium shifts to the left to increase the concentration back. More A and B are being formed. Effect of change in pressure. Equation is shown here. 2A plus B gives C plus D. Changes in pressure will only affect reactions between gases. When the pressure of a system is altered, system will respond to neutralize the change. When the pressure is increased by Le-Chatelier's principle, the position of equilibrium shifts to the right to reduce the total number of molecules and to decrease the pressure. When the pressure is decreased by Le-Chatelier's principle, the position of equilibrium shifts to the left to increase the total number of molecules and to increase the pressure. Effect of change in pressure. Increased pressure favors the reaction which produces fewer molecules. Decreased pressure favors the reaction which produces more molecules. If there are equal number of molecules on each side of the equation, changes in pressure will not affect the position of equilibrium. However, it will still affect the rate of reaction. Effect of change in temperature. A plus B gives C plus D. Delta H equals enthalpy change of forward reaction. If heat is introduced to the system will respond to neutralize the change either by absorbing or releasing heat. If delta H is greater than 0, then it's an endothermic reaction. When temperature is increased by Le-Chatelier's principle, the position of equilibrium shifts to the right to remove the extra heat. The endothermic reaction is favored. When temperature is reduced by Le-Chatelier's principle, the position of equilibrium shifts to left to release heat. The forward reaction and exothermic reaction is favored. Increased temperature favors endothermic reaction. Decreased temperature favors exothermic reaction. Effect of catalyst. Catalyst will not affect the position of equilibrium. This is because a catalyst increases both the rate of forward and reverse reaction. However, catalyst can speed up the time taken to reach equilibrium. Equilibrium constants Kc and Kp. Equilibrium constant is the value of the reaction quotient when the reaction has reached equilibrium. Alternatively, it can also be defined as a measure of the extent in which reactants are converted to products. At any given temperature, every reaction has a specific value of equilibrium constant, which is independent of changes in concentration, pressure, use of catalyst, or the amount of reactants you start with. Equilibrium constant expressed in concentration is called Kc, while expressed in partial pressure is called Kp. Equilibrium expression. A simple relationship that links Kc to the equilibrium concentrations or Kp to the equilibrium partial pressures of reactants and products, and the stoichiometric equation. The expression is shown here. For the equation AA plus BB gives Cc plus Dd, equilibrium constant in terms of concentration, Kc equals concentration of C raised to C times concentration of D raised to D over concentration of A raised to A times concentration of B raised to B. The square bracket shows concentrations in mole per dm cube. The indices are the numbers in front of each substance in the chemical equation. In equilibrium expressions involving a solid, we ignore the solid. This is because its concentration remains constant, however much solid is present. For example, Ag plus aqueous plus Fe2 plus aqueous gives Ag solid plus Fe3 plus aqueous. Equilibrium expression for this reaction is Kc equals concentration of Fe3 plus aqueous over concentration of Ag plus aqueous times concentration of Fe2 plus aqueous. Example, write an expression for Kc for the following reaction. N2 plus 3H2 gives 2NH3. Kc is given as concentration of NH3 raised to 2 over concentration of N2 times concentration of H2 raised to 3. State the units of Kc for this reaction. H2 plus I2 gives 2Hi. And the solution is shown here. Kc equals concentration of Hi square over concentration of H2 times concentration of I2. Units of Kc mole per dm cube times mole per dm cube over mole per dm cube times mole per dm cube. So no units for this equation. Another example. In this calculation, we are given the number of moles of each of the reactants and products at equilibrium together with the volume of the reaction mixture. Ethanol reacts with ethanoic acid to form ethyl ethanoate and water is shown here. 500 centimeter cube of the reaction mixture at equilibrium contained 0.235 mole of ethanoic acid and 0.0350 mole of ethanol, together with 0.182 mole of ethyl ethanoate and 0.182 mole of water. Use this data to calculate a value of Kc for this reaction. And the solution is shown here. Step 1. Write out the balanced chemical equation with concentrations beneath each substance. Step 2. Write the equilibrium constant for this reaction in terms of concentration. Step 3. Substitute the equilibrium concentrations into the expression. Step 4. Add the correct units by referring back to the equilibrium expression. Another example. In this example, we are only given the initial concentrations of the reactants and the equilibrium concentration of the product. A mixture of 0.0500 mole per dm cube propanol and 0.0500 mole per dm cube hydrogen cyanide is left to reach equilibrium at room temperature. At equilibrium, the concentration of the product is 0.0233 mole per dm cube. Calculate Kc for this reaction. And the solution is shown here. Step 1. Write out the balanced chemical equation with all the data underneath. Step 2. Calculate the equilibrium concentrations of the reactants. Step 3. Write the equilibrium constant for this reaction in terms of concentrations. Step 4. Substitute the equilibrium concentrations into the expression. Step 5. Add the correct units. Another example. In this example, you are given the initial and equilibrium concentrations of the reactants but not the products. Ethyl ethanoate is hydrolyzed by water. 0.1000 mole of ethyl ethanoate are added to 0.1000 mole of water. A little acid catalyst is added and the mixture made up to 1 dm cube with an inert solvent. At equilibrium, 0.0654 mole of water are present. Calculate Kc for this reaction. And the solution is given here. Step 1. Write out the balanced chemical equation with all the data. Step 2. Calculate the unknown concentrations. The chemical equation shows that 1 mole of CH3COOC into H5 reacts with 1 mole of water. So the equilibrium concentration is also 0.0654 mole per dm cube. The amount of water used in forming the products is 0.1000 minus 0.0654, which is equal to 0.0346 mole per dm cube. Step 3. Write the equilibrium constant for the reaction in terms of concentrations. Step 4. Substitute the equilibrium concentrations into the expression. Step 5. Add the correct units. Kc and concentration changes. If all other conditions remain constant, the value of Kc does not change when the concentration of reactants or products is altered. Explanation is given here. Kc and pressure changes. If all other conditions remain constant, the value of Kc does not change when the pressure is altered. Kc and temperature changes. In short, the equilibrium constants are constants at constant temperature. Only temperature can affect the value of Kc. For endothermic reaction, the value of Kc increases with increasing temperature. For exothermic reaction, the value of Kc decreases with increasing temperature. Equilibrium constant in terms of pressure. For reactions involving gases, equilibrium constant can be expressed in terms of partial pressures. For the equation AA plus BB gives CC plus DD, a Kp equals partial pressure of C raised to C times partial pressure D raised to D over partial pressure of A raised to A times partial pressure of B raised to B. The pressure exerted by any one gas in the mixture is called its partial pressure. Equilibrium constant in terms of pressure is shown here diagrammatically. Gas A and gas B. Partial pressure of gas A 8 Pascal, gas B 3 Pascal, total pressure 11 Pascal. The volume of containers are the same. For example, equilibrium expression for the reaction N2 plus 3H2 gives 2NH3 is written as Kp equals partial pressure of NH3 square over partial pressure of N2 times partial pressure of hydrogen raised to 3. An example is shown here. In this example, we are given the partial pressure of each gas in the mixture. The reaction to SO2 plus O2 gives to SO3. Equilibrium partial pressures at constant temperature. SO2 is 1 times 10 to the power 6 Pascal, O2 7 times 10 to the power 6 Pascal, SO3 8 times 10 to the power 6 Pascal. Calculate the value of Kp for this reaction. And the solution is given here. Step 1. Write the equilibrium expressions for the reaction in terms of partial pressures. Step 2. Substitute the equilibrium concentrations into the expression. Step 3. Add the correct units. Example, in this calculation, we are given the partial pressure of 2 of the 3 gases in the mixture as well as the total pressure. Nitrogen reacts with hydrogen to form ammonia. The pressure exerted by this mixture of hydrogen, nitrogen and ammonia at constant temperature is 2.000 times 10 to the power 7 Pascal. Under these conditions, the partial pressure of nitrogen is 1.490 times 10 to the power 7 Pascal and partial pressure of hydrogen is 0.400 times 10 to the power 7 Pascal. Calculate the value of Kp for this reaction. And the solution is shown here. Step 1. Calculate the partial pressure of ammonia. We know that the total pressure is the sum of the partial pressures. Step 2. Write the equilibrium expression for the reaction in terms of partial pressures. Step 3. Substitute the equilibrium concentrations into the expression. Step 4. Add the correct units. Partial pressure and mole fractions. Mole fraction equals number of moles of a particular gas over total number of moles of all the gases in a mixture. So, the mole fraction of ammonia in a mixture containing 0.5 mole ammonia, 0.9 mole hydrogen and 0.6 mole nitrogen is 0.5 over 0.5 plus 0.9 plus 0.6 equals 0.25. No units. The partial pressure is related to the mole fraction by the relationship partial pressure equals mole fraction times total pressure of all the gases in the mixture. Note that the sum of the mole fractions should add up to 1 and that the sum of the partial pressures should add up to the total pressure. Example, the equilibrium between hydrogen iodine and hydrogen iodide at 600 Kelvin is shown. H2 plus I2 gives 2Hi. At equilibrium, the number of moles present are H2 equals 1.71 times 10 to the power minus 3. I2 equals 2.91 times 10 to the power negative 3. Hi equals 1.65 times 10 to the power negative 2. Total pressure is 100 kilopascal. Calculate the value of Kp for this reaction. And the solution is shown here. Step 1. Calculate the total number of moles. Step 2. Calculate the mole fraction of each gas. Step 3. Calculate the partial pressure of each gas. Step 4. Write the equilibrium expression and substitute the values. Factors affecting the value of Kp. In short, equilibrium constants are constants at constant temperature. Only temperature can affect the value of Kp. For endothermic reaction, the value of Kp increases with increasing temperature. For exothermic reaction, the value of Kp decreases with increasing temperature. Importance of an understanding of dynamic equilibrium in the chemical industry and the application of Le Chatelier's principle. HABER process. Synthesis of ammonia is carried out by the HABER process. Equilibrium reaction involved is N2 plus 3H2 gives 2NH3 delta HR equals negative 92 kilojoules per mole. We can use Le Chatelier's principle to show how to get the best yield of ammonia. At high temperatures, when the reaction is faster, position of equilibrium is to left because the reaction is exothermic, delta H is negative. What happens if we increase the pressure? When we increase the pressure, reaction goes in the direction that results in fewer molecules of gas being formed. The equilibrium shifts in the direction that reduces the pressure. In this case, there are 4 molecules of gas on the left-hand side and 2 on the right-hand side. So the equilibrium shifts towards the right and the yield of ammonia increases. What happens if we decrease the temperature? A decrease in temperature decreases the energy of the surroundings. The reaction will go in the direction in which energy is released. Energy is released in the exothermic reaction in which the position of equilibrium favors ammonia production. This shifts the position of equilibrium to the right. The value of Kp increases. What happens if we remove ammonia by condensing it to a liquid? The position of equilibrium shifts to the right to replace the ammonia that has been removed. More ammonia is formed from hydrogen and nitrogen to keep the value of Kp constant. Contact process. The synthesis of sulfuric acid is carried out by the contact process. The main equilibrium reaction involved is 2SO2 plus O2 gives 2SO3. Delta HR equals negative 197 kilojoules per mole. We can use Le Chatelier's principle to show how to get the best yield of sulfur trioxide. What happens when we increase the pressure? When we increase the pressure, the reaction goes in the direction that results in fewer molecules of gas being formed. To reduce the pressure, there are 3 molecules of gas on the left-hand side and 2 on the right-hand side, so the equilibrium shifts towards the right. However, in practice, the reaction is carried out at just above atmospheric pressure. This is because the value of Kp is very high. The position of equilibrium is far over to the right, even at atmospheric pressure. Very high pressure is unnecessary and is not used as it is expensive. What happens if we decrease the temperature? Decreasing the temperature shifts the position of equilibrium to the right. A decrease in temperature decreases the energy of the surroundings, so the reaction will go in the direction in which energy is released. This is the exothermic reaction in which the position of equilibrium favors SO3 production. The value of Kp increases. SO3 is removed by absorbing it in 98% sulfuric acid. The SO3 reacts with the solution and eventually more H2SO4 is formed. Although the SO3 is absorbed in a continuous process, this does not affect the equilibrium significantly because the position of equilibrium is already far over to the right. That's all from me. Thank you so much for watching this video.